Good afternoon. Today I am going to be talking to you about how to challenge your children in mathematics. A few months ago we asked our parents what they needed most help with, and we've been creating videos each week to help you with these areas. So if you're interested in times tables, go to our website and find the relevant section. We've also created one about addition and subtraction, and we're going to be looking at division as well coming later on. So I'm going to share my screen and I'm going to talk you through a short PowerPoint I've prepared that's going to help to explain what we are, how we challenge in mathematics at Hanwell Fields. So, going deeper in maths, and notice I use that word going deeper. When we teach with a mastery approach, we're teaching the whole class, and we do that by enabling some children and recognizing that others are working at a certain level and others are able to go deeper in their understanding. What deep understanding is not. Only a few years ago, children who grasped a concept deeply were challenged by given larger numbers or next year's objectives. And I can remember having attending training courses where this was what we were told was how to challenge our children. We know now that just being able to grapple with a bigger number does not indicate that they're able to think deeply about a particular concept, but it does tell us that our children are good at number facts and often good at memorizing and making connections, which is a real strength in mathematics. Teaching with a mastery approach means that the class access the concept at the same time, but with different levels. Some children might use the working wall to support them with their number facts. Others might use jottings and resources in the class to help them with their understanding. But children working deeply can use different strategies to solve a calculation flexibly. They draw what they know using a range of representations. So they won't just be able to represent it using a bar model because that's what they're familiar with. They might be able to use a part whole, a number line, and make those connections. Explaining their thinking to a partner, the importance of this, I think, must be really emphasised. Being able to explain how you've worked something out is such a key indicator of your understanding, and being able to use the correct mathematical language to explain it. This shows that when they move up to the next year group or to secondary school, they're going to be able to access the mathematics because they've got the mathematical vocabulary. Giving an example that's not correct. Now that might seem like a really odd one, but to give an example that doesn't work in mathematics, you have to be able to tell me or know what's going to be accurate. So for example, if I were looking at number bonds to 10, 6 and 5, I know 5 isn't going to be a number bond to 10 because I know that 6 is an even number and two even numbers make an even number. So I know that an odd and an even number are never going to create an odd number. So the theory that goes behind that to give an incorrect answer, a misconception, shows a real deep understanding, and that's something we use quite a lot. Challenge a partner with a different answer to prove their accuracy. So in school, we have mixed ability pairings where children work together with their understanding. And I often say to them that if you've got a different answer, one of you needs to prove your answer. And the thinking that goes on behind that mathematics, explaining how they've worked something out, often can uncover a misconception. And it's in that discovery, in that explanation, that then enables us to maybe put a scaffolding to help them if it's working on a number fact, or to show them a model or representation. So that challenging and proving their accuracy. Being comfortable with having a go and potentially making a marvellous mistake. We often find children who are fluent with their number facts that recognise working quickly or think working quickly means they're a brilliant mathematician. And these are the children that want to finish first. And these are often the children that crumble if they get something wrong, if they don't see a page of pink ticks. Now, when I work in my class, I say to the children, if you see a page of pink ticks, I've probably not pitched the level hard enough because I haven't taught you anything. When you are able to have a go and you're able to make those mistakes, that is the part that we're looking for, that ability to be comfortable with this might not be the right answer, but this is a start. And that's a challenge for some children. Deep understanding is not about getting to an answer quickly or always getting it right. Handling uncertainty in maths is a tough concept. So when you're working at home and someone makes a mistake, just leave them to work out that and they can explain their thinking and actually allow them to figure out that the answer's wrong, and try to encourage that actually, whilst there are some aspects of maths, times tables, that we want that instant speed recall, often being the first to finish doesn't mean to say necessarily that you're the most accurate. While we're aiming for fluency, children need to make connections between known facts to work out what they don't know and evaluate a range of potential strategies. If, for example, I were adding 99 to 45, I wouldn't use a formal method of column addition. I'd want a child to know that they're going to round that 99 to 100 and add on one too many and adjust it after. So it's that manipulation of number that shows that a child has got a deep understanding. Using different strategies, I'm just going to give you a minute just to have a look at this calculation. So the first calculation, 674, is made of 600s, 7 10s and 4 1s. And that's what we call standard partitioning. We've partitioned into hundreds, tens and ones. When you look further down, 67 tens is a real deep understanding, because I've got to recognise that 60 tens is equivalent to 600 and 7 tens is equivalent to the 70. So you can see where that one activity could be really extended to show some non-standard partitioning and also children's place value understanding. Draw what they know using a range of representation. When we first started the mastery approach, the idea that we could draw our understanding seemed very alien, but now I often turn to a bar model or a part whole to help with my calculation. If we look at this calculation, if we look at this words problem, Danny has read 62 pages of the class book. Jack has read 43. How many more pages? Now I'm just going to use the pen here to show you the pivotal word, and it's how many more. So whereas you might have been used to seeing a bar model that was the traditional form where you've got the whole, you can see here how unstraight my drawing might be. This is my whole, and then I've got two parts, and the two parts make the whole. But this calculation, how many more, calls for a different understanding. It calls to recognise that one of my parts is going to be larger here. So Danny's read 62. I'm going to just write 62 there. That's Danny. And Jack has read 43. I'm going to give Jack a different colour to help us see the difference. Jack has read 43. So Jack's bar's going to be less. It's going to be shorter because he's read fewer books. 43. Now the question says, how many more books has Danny read than Jack? So it's actually asking us to find out the difference between the two calculation. And because I've drawn this calculation, now I can see that actually it's a subtraction. If I hadn't drawn it, it wouldn't underpin the structure of this words problem. And it might have led me to adding up 62 and 43, because that's the only form of bar model that I'd ever seen. I'd not seen the bar model where I'm calculating the difference. Flo does the calculation, 62 add 43. Jim does the calculation, who is correct. So actually being able to explain why, because I'm looking at the difference, you can see how this drawing of the representation would have helped me with that. Let's have a look at this word problem. So he's planting onions. He arranges the onions into rows of 4 and has 2 left over. So straight away, I want to draw that. I want to draw that to see. So some might get the counters and start drawing our rows of 4. Oh my goodness, you can see my rows of 4 aren't so great. So already I'm starting to think about odds and evens. Oh, that's a dreadful row. And then he's got 2 leftovers. I'm going to show my 2 left over in a different colour. I've got 2 left over. There they are. How many onions might he had? So now I can start to explore and see if there are any patterns. And this particular words problem is really open-ended, because it would allow us to see that, is it always the case that if I've got 8 and 10, so I've got 2 rows of 4 and he's got 2 left over. Now, if I had 3 rows of 4, I wonder what happens to the number. I wonder if I can start to make any generalization. So I've got 3 rows of 4 and 2 left over. That's going to give me the answer. So actually, this activity is so open-ended because it enables me to kind of look for connections. And these are the sorts of activities that children who are fluent and are quick in mathematics often don't like, because they're fairly open-ended. And these are the ones that would get that thinking developed. Now, this is a classic example of a non-example, of a misconception. So I can see my shape here, it's a square and it's divided into four shapes, into four. So I might talk about, actually, this shape is divided into quarters. So with this thinking, if I were to show this example, I would expect the children to say that actually they're right, it is divided into quarters. Some children might be able to recognise that actually the importance of quarters, of a fraction, is that they're equal parts. I'm dividing my whole into equal parts. So in exploring this non-example, I'd have to know, firstly, what a fraction is. I'd have to know that a fraction is a part of a whole. And it might enable me to come to the definition that a fraction is an equal part of a whole, and that then would be a worked STEM sentence that I could use in all of my workings. Challenge a partner with a different answer to prove their accuracy. So maybe when the children have got any homework, or when they've got a words problem, or if you're doing some cooking, if you've got a different answer, say to it, prove it. Instead of telling them they're wrong, prove it. That deep thinking that comes from possibly being correct, or that uncertainty, having to make connections, is where that deep learning happens. Be comfortable having a go. So let's have a look at this. For positive integers, and that's just a posh word for numbers, are the following statements always, sometimes, or never true? Oh goodness, there's a real open-ended here. The sum of two odd numbers is even. Now straight away you can see that word sum. So they're going to have to be comfortable with that mathematical language of a sum. Now sum, all sum means is just to add. And I know that sum means add because I've got a clear understanding of product, and the product of two numbers is a multiplication. So I know that sum means add because I've got clarity over my understanding of product. So I could explore this. How many examples would I have to give to decide if this was sometimes, always, and never true? Could I just say 4 plus 2 equals 6? Therefore, my answer's even, therefore it's always true. Is one example enough to prove that that's always true? Or would you expect them to be able to reason that by proving it with lots of different examples? How about if I used a multiple of 10? How about if that were now 40 and 20? Is that still true? Why is that true? And that depth of thinking that goes on. 40 add 20 equals 60. Oh gosh, that's a dreadful 6. Adding a 5 to a number ending in 6 will sum a number ending in 1. So this could be a whole lesson, a whole exploration about what happens when we add different numbers. And you can see there, explain why in every case, that emphasis upon what I know about number bonds. So for example, for this question, adding a 5 to a number ending in a 6, I would be expecting children to say that I know that 5 add 5 equals 10, then number bonds to 10. So one more is going to always give me a 1 in the ones column. And notice how I've used the 1 in the ones column, and it's thinking about that language that the children are using to explain their understanding. And lastly and finally, in this short video about how to challenge your children to go deep in maths, is we want children to have inquiring minds and be challenged. We want them to be afraid because that's where the learning happens.